Okay, so x86 assembly language is a family of assembly languages that provide backwards compatibility ranging all the way back to the Intel 8008. You can't go further back than that. You can't write code for an Apple II or a Motorola CPU. You can't go to an IBM mainframe or something. It only goes all the way back to the Intel 8008. It's named the x86 because the first processor to use the language was Intel's 8086. So, if you want to know what the 8008 was... Oops, I just switched this. Okay, there we go. The 8008 was a chip created by Ted Hoff after he crammed 2,300 transistors into a 1/6 inch by 1/8 inch chip in 1972. The chip was called the 4004, and then shortly after the 8008 was made, an 8-bit processor. It pretty much became the industry standard, and it was the thing that got Intel out of their little DRAM business. So one reason you would really want to know how to do assembly language, specifically this assembly language, is because it's really good for debugging. If you want to write a kernel, you'll need to know assembly language. Even though it's not x86 specifically, if you're doing homebrew development for older games, you would want to know some kind of assembly language. So the thing that a lot of people get confused on is all these names right here, they're essentially the same thing. They're just by different processor manufacturers. So I will read what I have here. It says, even though these names all look very different, they are fundamentally the same thing. x64 is just a generic name for the 64-bit extensions to AMD's and Intel's x86 instruction set architecture. That's what ISA means. AMD was the first to introduce x64. Intel was originally called... Oh wait, no. It says... which was originally called x86 64, and then later it was renamed to AMD 64. Later, Intel named their implementation IA32E, and then EMT64. There are really slight incompatibilities between the two. They're mostly the same. 90% of code will be the same. And then down here we have IA32, which was AMD didn't have their own little extension. They usually just used the IA32, their earlier processors, but just like the names above, these names are fundamentally the same. Sometimes referred to as the i386, the IA32 instruction set architecture is simply a 32-bit version of the x86 instruction set architecture. So, just a review of the data types that you will find in the Intel manuals. So, here we have 8 bits, which is a byte, 16 bits, which is a word, which is just a unit of data, it's not a literal word. You have 32 bits, which is a double word or a D word, and you have 64 bits, which is a quad word, and then you have 128 bits, which is a double quad word. You will usually see, if you do later when I'll be coding in assembly language, you will see D word in the code. So the architecture for specifically Intel, or not specifically, but for most processors now, is little endian, meaning that the lower significant bytes are stored in lower memory addresses. In the Jonathan Swift book, Gulliver's Travels, big endians are at war with the little endians over whether to crack eggs from the big end or the little end. The choice is totally arbitrary, but that's kind of the joke. It was supposed to be an allegory for certain wars that were going on at the time. I think it was between the French and the English, I don't know. But CPU designers have a similarly arbitrary choice to make regarding how bytes in the CPU register get copied to and from memory. If I was going into little endian, which is to the right here, I would take the least significant byte, which, let's say it's this, and then I would copy it into the lowest register. But if I was doing big endian, I would take the biggest byte, which is this, and put it into the lowest register. It's not super complicated. So one thing I actually got confused about, I had to ask somebody, but the reason why a byte may be more significant than any other can be explained by any positional numeric system. For example, if you take the number 51354 in base 10, the first 5 is more significant because it stands for 5 multiplied by 10,000, while the second 5 is just 5 multiplied by 10. When you deal with computers, most of the time numbers will be fixed width. As another example, 16-bit unsigned integer can be thought of as a sequence of 16 binary digits, with the left one being the most significant and the right one being the least significant. So now onto registers. Not to be confused with caches, because I know caches are also pretty quick small storage spaces, like temporary storage spaces available on the CPU. But a processor register is just a small storage space available to our computer CPU. It's quickly accessible location and is a feature of almost all computers. Most computers have registers, or general purpose registers. You can load data into them, perform some computations, save the results into to a more permanent memory location such as RAM, even though RAM isn't really that permanent, but it's a lot more permanent than a register. Data registers inside an x86 CPU maintain backwards compatibility thanks to the fact that their upper and lower halves are separately addressable. In English, that means a register inside a 64-bit CPU can be used interchangeably as a 32-bit register by simply splitting the 64-bit register into subsets. This is what allows 32-bit code to run on 64-bit machines. That's why it doesn't, blow up if you try to run a 32-bit program on a 64-bit processor. The data registers, as well as the pointer and index registers, can participate in most arithmetic and logic operations. Despite there being a primary accumulator, all 8 general-purpose registers GPR fit the definition of accumulator as used in first and second generation microprocessors. That last bit of information was probably not that useful, but I thought it was interesting. I was reading the 8086 manual, and I just included that in there. The main 8 registers introduced in x86 CPUs are... So right here what I have is the different names for the different machines. So AX is what you would call the register in a 16-bit CPU. EAX is what you would call the AX register in a 32-bit CPU. The E stands for extended. And the RAX is what you would call the AX register in a 64-bit machine. So when you are coding certain, when you're making 32-bit code or 16-bit code or 64-bit code, you have to specify the right register name, otherwise you'll be in trouble. So AX is the primary accumulator. It is used in input-output and performs most arithmetic instructions. The x86 manual just says it is word multiply, word divide, and word input-output. So the BX is the base register. It's a pointer to the data section, and if you don't know what a pointer is, I have it listed here. It says a pointer is a variable that contains a memory address. The BX register in particular is often used in position-independent code, or GCC, I think. So the CX register is a counter register. It is the counter for string and loop operations. The Intel 8086 manual just says it's for string operations and loops. I find that the Intel 8086 manual has a pretty minimalistic description of things. So the DX register, or the data register, is used as an I/O pointer, performs some arithmetic and interrupt calls. It is used with the AX register to multiply and divide operations involving large values. The Intel 8086 manual just describes it as word multiply, word divide, and indirect input-output. So I have the source pointer and the destination pointer together because they kind of rely on each other a little bit. So one is they're both pointers. So they're pointers for string operations. Instructions or string operations may be copied from SI to DI or from source to destination. The stack pointer, which is it's pretty important, is the pointer for stack operations, and it holds the top of the address of the stack. And the base pointer is the pointer to the base, pointer to the data, or just pointer to data on the stack, and it holds the base address of the stack. Now flags it's just a register. If I was working in a 32-bit machine, it would be E flags, and if I was working in 64-bit machines, you can guess it'll be R flags. So The flags register holds multiple different single-bit flags. I have the addresses right there, 0, 2, 4, 6, 7, and 11. The series of single bits in this register, oh, that got cut out by the screen, sorry, all have names. For example, there is a bit called the 0 flag. There will be a very specific position in flags that corresponds to the 0 flag. Typically, whenever the CPU is doing any calculations, the result of the calculation will be indicated in the flags register. Just as an example, if you decide to perform an add instruction and you added 3 to -3, the result will be 0 and the 0 flag will be set. Most arithmetic instructions, such as the sub, mul, and div, can set a flag, or subtract, multiply, and divide. For the sake of brevity, I will go over the main 6 flags. There are like 2 others in 64-bit x86, but I'm not going to go over them for the sake of brevity. So the AF, the bit address for this is 4. The adjust flag, this flag is used by decimal arithmetic instructions and denotes binary coded decimal in byte carry. The carry flag, this flag is used if the operation generated a carry or borrow. It's primarily used by instructions that add or subtract, because you usually need to carry or borrow and add and subtracts. The overflow flag, this flag is set in arithmetic if this flag is set, an arithmetic overflow has occurred. What this means is that a significant digit has been lost because the size of the result exceeded the capacity of its original destination. Usually in the older version of Windows, when you get the blue screen of death, it was because of an overflow, or stack overflow. So the SF is the sign flag. This flag is set if the most significant bit of the result is 1. 0 indicates the positive value and 1 indicates a negative value. So then we have PF. Sorry, I forgot. The SF address is bit 7 and the OF address is bit 11. The PF parity flag, parity flag. This flag is used to set the least significant byte of the result, this flag is set. If this flag is set, the least significant byte of the result contains an even number of 1 bits. This flag can be used to check for data transmission errors, and it usually is. The 0 flag, like I talked about up there, is just a flag that's set if the operation is 0, or the result of the operation. So sorry you can't see, some of this paragraph is cut out. So the stack is a data structure that manages data and values in a last-in, first-out manner, which this means that the last element you put on the stack is the first element that will come out. One could think of the stack as a stack of papers on a desk. When a piece of paper is added to the stack, it is placed on top of all the other papers. If you want to grab a piece of paper, you can only grab the one that's on top. These are 2 fundamental operations of the stack. You access, read, or write data only at the top of the stack. To read data is to pop, and to write data is to push. The instructions used to implement a subroutine, or callable unit, if you're not familiar with the term subroutine. Callable unit is just a general term for the same thing. Call and return are the call and ret instructions. Ret meaning return, obviously. First, the call instruction pushes the current code location onto the stack, and then it performs an unconditional jump to the code location indicated by the label operand. Unlike the regular jump instruction that you will use in x86 assembly language, a subroutine callable unit return mechanism. The return instruction implements a subroutine/callable unit return mechanism. The instruction first pops a code location off the stack, and then it performs an unconditional jump to the retrieved code location. As previously mentioned, the current top of the stack is pointed to by the SP pointer, or the stack pointer, like I mentioned up here with all the pointers and registers. The stack grows downward from high to low memory addresses, resulting in any recently pushed value appearing in memory addresses above the SP register. There is no data register that points to, or just no register that points to the bottom of the stack. However, most operating systems monitor the stack bounds to detect underflow, popping an empty stack, or overflow, pushing too much information onto an empty stack. Like I said, this overflow, stack overflow, is a thing that will happen if you. Oh, it's usually what happens if you get a blue screen of death in a earlier version of Windows or something like that. I don't know if it still happens. So here, down here, I have examples of the syntax. So when I have region or register 64, this just means any 64-bit register, and then I have any 64-bit constant, and then a memory address. So when you're using the push command, you can push like any register. You could push a memory address, or you could push a constant. You can pop a 64-bit register. You could pop a memory address. When you're calling, you can usually just put anything inside this label, just any label that you really have to call, and then you just return. There's nothing really that comes after that. I was going to put segment registers into this, but the current 64-bit mode of assembly language no longer supports this stuff. I might put it in the next one, I'm not sure, but for now, my voice is starting to get tired.